I want to introduce about the Faraday's law. So Faraday's law, I have already said that it is nothing but the measurement of the induced EMF. So when there is a change in the magnetic flux, that means d phi dt is there. Change is always with respect to time. D phi dt. So whenever the d phi dt part is there, passing through an area bounded by the closed conducting loop, and EMF is generated, that is known as the induced EMF. Induced EMF. So the induced EMF is produced due to only the change in the magnetic flux. If there is no change in magnetic flux, then there is no induced EMF. In this setup, what I am doing, so as I move the copper wire inside this tube, so gradually as I moving the wire up and down, that means I am creating the change in flux. I am creating there is a solenoid. So once the solenoid is being inserted inside this copper tube, that means I am inserting the copper tube, inserting the solenoid inside the copper tube, means I am changing the flux. Once I am changing the flux, what I can see the galvanometer deflection. Okay. So galvanometer deflection is being observed. Why? Because by raising or moving up and down the solenoid coil inside the copper tube, I am going to change the magnetic flux. So that means there is an induced current. Okay. So this is the formula that I am going to use, that is equals to minus d phi with the minus sign. But again, in order to do the numerical, you don't have to consider the negative sign. So when there is a change in magnetic flux passing through the area bounded by a closed conducting loop, so this loop should be closed. Okay, it should not be open loop. Okay, induced EMF is being produced. Induced EMF is being produced, and if the loop is closed, then only I can see the current. Otherwise, I cannot see. Okay, if the loop is open, then the current will be zero. For the closed loop only, the current will be flow. Okay. Now, induced EMF exists for that duration in which the flux change. So once I move the magnet inside this coil, now at some point, if I keep the magnet fixed inside the coil, that means I am not changing the position of the magnet. That means at this position, the V of the magnet is zero. V is zero. That means there is no change in the flux. So what is the flux? That is constant. So for this period, you can clearly see the magnetic flux is zero, and correspondingly there is no change in the magnetic flux. That means the I is also zero. Okay. So once I keep the magnet inside the steady position or fixed position within the coil, and I am ensuring that there is no change in the flux parameter, that means what you can conclude that in this situation, the I should be equal to zero. Okay. So flux is not going to change. Now, how fast the magnet is moving, that is also important. That is also important. Why? Because faster moving the magnet means greater change in the flux parameter. Okay. And when rate of change of flux is more. So if the rate of change of flux is more, that is going to induce the induced EMF, changing the induced EMF very fast. Because every time, as the current is changing a direction, induced EMF is also changing the direction. One way is clockwise, another way is anti-clockwise. Okay. So induced EMF is in a closed loop. Closed loop is important because to the negative time or rate change of the magnetic flux to the loop. That is the statement of the Faraday's law. So EMF will produce only when phi b varies. Phi varies. If I say in this situation, if B is a magnetic field, varies. Because in order to change the phi b, either I can change the B, or I can change the A, or I can change the theta. Okay. Either by changing any one of the parameter, what you can ensure that the flux is going to change. That the flux is going to change. So once I say that in this situation, if I increase the current or decrease the current, or increase the magnetic field or decrease the magnetic field, so whenever I am changing the magnetic field, that means now the flux is going to change. Flux is going to change. So in this situation, the magnetic flux is changed by changing the B value. B value. If I vary the area, as the loop is moving up and down, so in this situation, magnetic field is constant. So whatever the magnetic field lines are there, that is from north to south pole in this direction. So B number is constant. I am not changing the B number. So as the loop is moving down, that means I am changing the area. So by changing the area also, I can ensure that the current will flow. Why? Because phi will change. And if I move this, so gradually the rod is moving, that means it will increase the area. It will increase the area. So as the area increases, then also the current will flow. Similarly, if I rotate it, if the coil is being rotated, now in this situation theta is changing. Okay. So either by changing V, A and theta, I can change the magnetic flux. And once I change the magnetic flux, that means every time the epsilon will be generated. Okay. Now direction of the induced current. So induced current direction has to be calculated based on the length. Okay. Now there is another segment, how to calculate the induced current. So for that, I should use the Faraday's law also. So first take the direction of the loop and A vector along the existing B. Okay. Let us say there is a field which is cross. And I place a loop inside this. Let us say this is the loop. So in order to make the A to be in the cross direction, I move the loop in this clockwise direction. Okay. So that means I also assume that A is in this cross direction. Okay. Now find phi equals to B dot A. Now if I say in this situation, let us say B is changing, B is increasing. So phi is also equals to B into A, and that is also increasing. Okay. So if d phi dt number is positive, here d phi dt is positive, that means current is opposite of the assigned direction, step number 1. What is the step number 1? Step number 1 is assigned direction in this direction. If I say this is the direction. Why? Because if I say along the clockwise direction, the current is being flowing, that means A is cross. Along the clockwise direction, if the current is being flowing, A is cross. Why A has to be kept cross? Because I have said, taken that B is cross. The first step is assign the direction and then calculate the phi value. If you found that d phi dt is positive, d phi dt is positive, the induced current is opposite to that assigned direction. That means induced current will be in the opposite direction. So you can verify this statement by Lenz's law also. If in this situation cross magnetic field is increasing, so increasing cross magnetic field, opposing effect is increasing dot number. Okay, so dot number has to be increased. That means the current, induced current has to flow in the direction. Okay, and the opposite to the assigned direction. Now, if d phi dt are found to be the negative one, then induced current should be in the same direction as that of the step number 1. So this is another way to calculate the induced current direction. Okay, based on the Faraday's law. So based on the Faraday's law, you can also calculate, or based on the our Lenz's law. But once we calculate the epsilon induced, so correspondingly, if I say R is the loop resistance, because loop is made of some material, so for that material, if the rho number is given, so R can also be written as the rho L by A number. Okay. So that A is the area of cross section of this wire. Let us say the area of cross section is given as A number, material is rho, length of the wire is L. So based on that, I can calculate the rho L by A number, that is the resistance of the loop. Once I calculate the resistance of the loop, now I can calculate what is the current that is flowing through the loop. That should be equals to induced EMF and divided by R number. So that current is nothing but the induced current. So that can only be calculated if I know the epsilon. Once I calculate the epsilon number, then only I can calculate what is the current that is going through there. Okay. So mathematically, I can write this way: is 1 by R into minus d phi by dt. But this minus sign is not significant for this calculation, because every time I direction has to be calculated based on either Faraday's law or by Lenz's law. Which one is better? Any law I can apply. Okay. So induced EMF give rise to the induced current. So this is induced, this is also induced. Okay. Now important point regarding the induced EMF is that, so induced EMF does not depend on the nature of the coil and its resistance. Why? Because inside the induced EMF only the d phi dt matters. So phi is not dependent on the material property. Okay. Which material is used to produce this wire is not important. But that means the rho, L, A, these are not important for the phi number. So phi depends entirely on the B, A and theta. Yeah. So based on this phi number, induced EMF is dependent. So induced EMF does not depend on the nature of the coil. But induced EMF exists in open circuit also. Whenever there is a change in the flux parameter, that means the EMF is being generated. If I say I take an open coil like this. Okay. So open coil, this point. So if I increase this B number through this area, that means the flux is going to change. So once I ensure that the flux is changing within that area, that means what you can say, now the induced effect is being produced. That means induced EMF is there. But induced current is dependent on the resistance of the coil. Why? Because inside this induced current, the R number will come. And R is material property. Okay. And magnitude of induced EMF is directly proportional to the relative speed of the coil magnet system. That means how fast they are moving. How fast they are moving. So induced EMF is varying for the open circuit also. If the circuit is open, then also the induced EMF being generated. But whether the current will flow or not, that depends whether the circuit flows or not. In this situation, I induced is how much? I induced is 0. No current is being flowed. Why? Because the circuit is open. This part is open. So once the circuit is open, no amount of current is being flowing. Okay. But once I close the circuit, now the current will start to flow. But induced effect are dependent on material property, induced current, but EMF is not dependent. Let us say the B is changing with this parameter, B naught into T square. Okay. Now you want to calculate what is the induced current. So corresponding to that, phi is how much? Phi equals to B naught into T square into area. Area is how much? If I say the radius of the loop is R and I took theta is 0 dB. Why? Because since B is dot, I assume that A is also dot. A is assumed to be dot. So that is equals to B naught into T square into pi into, let us say, capital R square. Okay. So that means phi is a function of time. So once I get the information that phi is a function of time, now I can calculate d phi dt number. What is that number? That should be equal to B naught into pi capital R square into T. That is the d phi dt. So correspondingly, what is the current? That I current should be equals to d phi dt by capital small r, because small r is the loop resistance. So B naught pi R square, here is small r, into 2T. That is the current. Now regarding the direction, as time increases, so B is going to increase. So that means dot magnetic field is increased. Dot magnetic field is increased. So opposing effect is dot has to decrease. Dot has to decrease. But decrease is not possible. So what you produce? You produce the cross to be increased. So cross to be increased, that means in this direction, cross magnetic field has to be increased. That means the current has to flow in this direction. Okay. So current is along the clockwise direction. That is according to the Lenz's law. If I follow the other law, that is the Faraday's law, so initially I have to give one direction. So corresponding dot magnetic field, I have to put the direction in the anti-clockwise direction. So if I say this is the I direction, then only I can say A is dot. Okay. So once you put this I direction, correspondingly I am getting A equals to dot number. Now calculate the phi number. So d phi dt will be the same answer. D phi dt will be the same answer, that is B naught into pi R square into T. So d phi dt calculation is not depending on the direction. But once I say that B is increasing, so d phi dt will increase. So that means what you can say, d phi dt number is positive. Now once the number comes to positive, that means you have to change the direction. Okay. So change the direction means correct direction should be in this direction. So that is the I induced. If you get the d phi dt number as negative 1, then the assigned direction is the correct one. You don't have to change it. Okay. So in order to check the direction from the Faraday's law, the steps are more. Steps are more. But once you check the direction with the help of Lenz's law, the steps are less. And it is easier to understand also. So every time you prefer to apply the Lenz's law, but it is also advisable to learn how to check the direction using the Faraday's. Okay. Now you are asking to calculate the charge flown through the loop. Okay. So whenever the current is being flowing, that means there is some kind of charge is also flowing. So, okay. So for that again I should do the same experiment. So phi is how much? Phi is equals to B naught into T cube into area of loop is, let us say, A. Okay. So d phi dt is what? So d phi dt should be equal to B naught A into 3T square. That is epsilon induced. Okay. So correspondingly I current is how much? I is equal to epsilon induced divided by capital R, small r. Okay. That's because of C V naught A T square by small r. That is the current that is flowing through the loop. So if the current is this one, so corresponding what is the charge flowing? So I should be equal to dq dt. I should be equal to dq dt. So once you do the integration, so that should be equal to 3 V naught A by R integration T square dt. Integration T square dt. So at t equals to 0, there is no charge in flowing. At t equals to t, what is the charge? That is the Q. So that you want to calculate. So from the left part, so I am getting Q number, that's to the 3 V naught A divided by R into T cube by 3. So ultimately 3 cancels. So what I am getting? V naught A T cube by R. So there is one way to calculate the charge flowing. How much amount of charge is flowing through the circuit is one way. But this way is not so much popular. Why? Because once we do the differentiation, first to do the differentiation, then you do the integration. That means back to the same result. Back to the same result. So instead of doing this, what I can see that I can do it in alternative way. Let us say what is the charge flowing. So again the question is saying that what is the amount of charge flowing through the circuit. So what I am going to calculate the initial flux. Why? So phi initial. Phi initial is what? Phi initial is at 0 time. Phi initial is at t equals to 0. So at t equals to 0, flux is how much? Flux is 0. Why? Because at t equals to 0, V is 0. So phi final. What is phi final? That is equals to t equals to t naught. So that should be equal to V naught into t naught cube into area of loop. So what is the change in flux? The delta phi is what? That is the change in flux. That should be phi final minus phi initial. That means phi final minus phi initial. That should be how much? V naught T cube into A. That is the change in flux. Now change in flux. What is the change in flux? Delta phi. So divided by R, loop resistance. So if I want to calculate the Q number, Q can be calculated by delta phi by small r. Small r is the resistance. Okay. So that should be equals to V naught T cube into A by Y. Because if I do the differentiation, so dq dt should be equal to how much? D phi dt divided by 1 upon R. So that number is how much? That number is I induced. Okay. And that is equal to dq dt. So that means without doing any kind of integration or differentiation, I can calculate the Q number by simply calculating the total change in flux. Answer remains same, that is V naught T cube A divided by R. So what I calculate over here is the total change in flux. How much amount of flux is being changed. And whenever you want to calculate the total change in flux, that means phi final minus phi initial. The final is at T naught time, initial is at T equals to 0. Depending on the expression given, so you have to calculate the total change in flux. So once I calculate the total change in flux, divide by loop resistance, that will be the total charge.